Greetings. In this video, we shall delve deeply into the positional decimal numbering system. In our previous lesson, we explored the fascinating history of numeral systems, including the origins of the Indo-Arabic system. We discovered that this remarkable system was first developed in the region that is now modern-day India and later adopted, refined, and disseminated by scholars of the Muslim world. Furthermore, we learned about the transformative work of Fibonacci, who, in the early 13th century, published a groundbreaking book that would forever change Western civilization, Liber Abaci, in 1221. Before Fibonacci's influential publication, Europeans primarily relied on the Roman numeral system, a system of historical significance but one fraught with limitations, particularly in mathematical applications. These inefficiencies posed substantial barriers to mathematical advancement. Through Liber Abaci, Fibonacci demonstrated, with compelling examples, the versatility of the Indo-Arabic system, convincing Europeans of its superiority. In this video, we shall examine how numbers are represented in the decimal positional system and explore the principles of addition and subtraction. While this may seem deceptively simple, our discussion will serve as a foundation for understanding systems with bases other than 10. Let us now embark on a journey to uncover the elegance of the positional decimal system. In a simple tallying system, numbers are represented by marks. For example, 4 objects would be denoted by 4 tally marks. The positional system, however, employs symbols to represent quantities. For instance, 1 object is represented by the symbol 1, 2 objects by 2, 3 objects by 3, and so forth. This system progresses through the symbols for numbers 1 to 9 to 1, 2, 3, 4, 5, 6, 7, 8, 9. At this point, there is a natural temptation to create new symbols for numbers greater than 9, perhaps a star for 10, a triangle for 11, and so on. However, creating an infinite number of symbols is impractical, as it would require memorizing an endless array of unique representations. So, what ingenious solution did the inventors of the positional system devise? They introduced one of the most profound inventions in human history, the number 0. This 0 was represented by a simple, round, or oval shape, perhaps symbolizing a void or emptiness. To better illustrate this system, we can use a charming teaching tool, the abacus. You may recall that an abacus consists of a physical frame with rows of wires, each strung with beads. Let us consider the top wire, which contains 9 beads. These beads will represent the units in a number. By moving 1 bead to the right, we represent the number 1, 1 unit, 0 tens, and 0 hundreds. Moving a second bead represents 2, and a third represents 3. Continuing this pattern, moving 8 beads represents 8, and 9 beads represent 9. Now, here is the brilliance of the system. We do not create a new symbol for the number 10. The abacus used to demonstrate the Indo-Arabic numeral system may have either 9 or 10 beads per wire. For our purposes, we have chosen one with 9 beads on each wire. Here, we begin with a number represented by 0 hundreds, 0 tens, and 9 units. To produce the next number, we would need to bring one more bead from the left to the right, completing a total of 10 beads. However, since our abacus is the type with only 9 beads per wire, we shall employ an imaginary bead, envisioning it joining the existing 9 beads to form a group of 10. I will represent this imaginary bead here with a different color for clarity. So, what do we do next? We group these 10 beads, 9 physical and 1 imaginary, into a single, distinct bead. This new bead represents the value of 10 beads from the initial group. Observe as we move 10 beads back to the left. These 10 beads are then represented by a single bead in the tens wire, signifying a value of 10 units. Finally, we move this bead, representing 110, to the right. The result is the number 10, which literally means 110 and 0 units. And here we encounter one of the most profound innovations in human history: the invention of the number 0. 0 allows us to signify that the unit's place is empty, while indicating that the tens place contains one element. Let us continue counting. To reach 11, we move 1 bead from the unit's wire to the right. This gives us the number 11, representing 110 and 1 unit. Next comes 12, then 13, and so on, until we reach 19. Here, we encounter a pivotal moment. By adding 1 to 19, we group these 10 units into a single bead representing 110. We reset the units to 0 and move this new 10 to the tens place. The result, the number 20. Now, for simplicity, I shall tilt the abacus 90 degrees. Like this. This adjustment makes it easier to visualize the numbers. In this new orientation, the number 20 appears as follows. To form 21, we move a single bead from the units to the lower position. And 22, precisely, like this. We continue until we reach 29. And then, what comes next? That's right, 30. Progressing further, let us consider the number 99. What happens when we add one more? At this point, we group these 9 beads, along with an imaginary bead, into 10 beads. These 10 beads are then represented by a single bead in the tens wire. Next, we move this bead into the tens place, resetting the units to 0. Now, the 9 tens are grouped with the newly added 10, forming 100. This is represented by a bead in the hundreds wire, while the tens place is reset to 0. We have reached the number 100. From here, we continue, 101, 102, and onward until 109. Then 110, 111, and so on, until we reach 199. What happens next? Yes, the result is the number 200. At this point, let us set aside the abacus and rely solely on the written representation of numbers. We progress, 201, 202, and so on, until we reach 299. And after that, 300. Now consider what happens when we reach 999. Precisely, we arrive at 1000. This is the essence of the decimal positional system. With this understanding, the abacus becomes unnecessary. Indeed, Indian and Arabic mathematicians abandoned the abacus early on, as written notation proved more efficient. A fascinating detail. While Fibonacci's Liber Abaci is often translated as the Book of the Abacus, most scholars agree it is better rendered as the Book of Calculation. Let us continue with an exercise. Consider the number 4917. What does it represent? Think carefully and write your answer. Have you found it? This number consists of 4 thousands, 9 hundreds, 110, and 7 units. There is another way to express this number. Recall that 100 equals 10 squared, and 1000 equals 10 cubed. Thus, 4917 can be written as 4 times 10 cubed, plus 9 times 10 squared, plus 1 times 10 to the first power, plus 7. This, my friends, is the true meaning of a decimal number. The finale, why base 10? Let us return to a question posed earlier in this video. Why did the inventors of the Indo-Arabic numeral system choose to group numbers in sets of 10? Do you recall the answer? Precisely. We are naturally familiar with the number 10 because it is the one we encounter most frequently throughout our lives. It is the number of fingers on our hands. This choice is not only intuitive but also remarkably practical. In fact, many other cultures, independently, developed numeral systems based on 10. However, it is important to note that other systems do not possess the same efficiency as the Indo-Arabic system. Take, for example, the Roman numeral system. In its own way, it also organizes numbers into groupings of 10 objects. Systems like these, which group numbers in tens, are collectively known as base 10 systems. But here's an intriguing question. Are there systems that do not use base 10? The answer is a resounding yes. Many such systems exist. Consider these examples. The Babylonians, for instance, used base 60. We can still see the influence of their system in modern life. Our clocks measure time in 60 seconds per minute and 60 minutes per hour, and circles are divided into 360 degrees. Some cultures used base 12 numeral systems. This tradition has left its mark as well, such as the continued use of dozens in counting today. In Oceania, certain indigenous systems utilized base 2 and other bases. Yet, the primary reason we study bases other than 10 lies in the realm of computing. Computers do not operate using base 10. Instead, they primarily use base 2, where only 2 digits exist, 0 and 1. Additionally, computers sometimes employ base 8 and base 16 for specific applications. In our next video lecture, we will explore these alternative bases in detail, with a particular focus on the binary system. The application of this system in constructing modern computers was first proposed by the brilliant polymath Claude Shannon, a topic we will delve into in subsequent videos. In this video, we focused on the fundamental workings of the Indo-Arabic numeral system. While the topics covered here may have felt overly simple at times, we hope they serve as a foundation for understanding the more advanced discussions to come. We look forward to seeing you in the next video, where we will explore other fascinating numeral systems. Until then, farewell to all.